now to the last presentation before the coffee break, and we move to the United States. And this will be given by Iain Walker, who is a senior researcher at Lawrence Berkeley National Laboratory. He's also an AIVC board member for the United States, and he is also, and I think that's very relevant for his presentation, he's a previous chair of the ASHRAE Committee 60.2 on residential ventilation. So I think he's very well placed to tell us about ventilation standards and regulations in the United States.
Hello, everybody. I'm going to change directions a little bit here once we've dealt with some technical issues and talk a little less specifically about energy, but more specifically about ventilation and ventilation standards, but mostly from a US perspective. Hello? Oh, yeah. One moment, please. Well, I can start talking while this is happening, right? I think that's going to be okay. Thank you. So I think a key thing here is that in the US anyway, we have this idea that ventilation is primarily about indoor air quality, right? How do we achieve good indoor air quality? We talk about things like airflow rates, filtration requirements, operational issues like how noisy is your fan, how well is it controlled, and so on. But from an energy perspective, we think about airtightness, mostly because we want to control the airflows in and out of a building, know what they are, limit them for energy purposes. We think about how leaky is a building envelope. We look at how the wind and temperature differences turn those leaks in the envelope of a building into airflows and so on. We have standards in the US for energy control from air tightness perspectives. We use the metric of air changes per hour at 50 pascals. Most of the country in the US, you have to be 3 or less. For commercial buildings, we do it in a slightly different way. Rather than thinking about it volumetrically, it's more of a quality control aspect sort of thing, where we think about how well is the envelope constructed. So we have this idea of normalizing by the exterior area of the building. And that's quite common in other countries also, is to split things in this way. And I'm going to have one note before I get into the details here, that we don't have a national building code in the US. It's state by state, jurisdiction by jurisdiction. Each town or county decides what it's going to do. And this applies also to these issues of air tightness and ventilation. And there's a lot of what we call above code programs, which means that it's not just the regulation that says what's the worst building you can build. It's ideas about how do you do better. And these things are also often referenced there. These are the two standards we have in the US for ventilation. One is for non-residential buildings. One is for residential buildings. The changes are in the title. It's pretty obvious. And I'm going to spend the next few minutes talking about some of the similarities and differences between these two. But effectively, these are the national standards for ventilation in the US, even though they're not government documents. They're promulgated by ASHRAE, but they're adopted by various code bodies. So I'll start out with the one I know best, which is ASHRAE 62.2 that I was chair of for many years. And it's basically a standard that says how much airflow do I have to move in order to minimally meet some sort of indoor air quality that would be acceptable. And acceptable, broadly speaking, includes controlling for odors, controlling for moisture, controlling for health. Although we don't separate those things out necessarily in the standard, we just say, here's an airflow. We use an equation. I think there's probably quite a few engineers in the room. We love an equation or two. And we say, if you know the floor area of the building and you know the number of people in it, this is the sort of airflow that is required. We have a proxy for number of occupants, which is number of bedrooms plus one, pretty straightforward. But the odd thing that we do in the US that almost no other ventilation standards do is we allow you to account for how leaky the home is that you are ventilating. And, you know, engineers, we love some equations, right? We have what we call a credit for natural infiltration, which says if you've measured how leaky the building is, we're going to use some calculation procedures to turn it into an airflow. And you can put in a smaller ventilation system if you have a leaky building. And I know it sounds very counterintuitive, right? It seems like, what are we doing here? And in fact, this has created very, very strange things in the US. We have weatherization programs that go into existing homes in low-income communities and upgrade them by insulating them or putting in better heating and cooling equipment, and often air tightening. But they only often air tighten down to the limit where if they made the building tighter, they would have to put a fan in. And it's partially wrapped up in this idea of giving credit for how leaky the building is. Now, we could debate all day whether that's a good idea, but it is an unusual thing that most countries' ventilation regulations do not do that. They just specify a fan flow rate. In the US, we have this slightly different way of doing it. And I'm not going to get into the details of the calculations, but it has things like tables of locations. And the column I've highlighted there is a little weather factor that says, we know that even if you have the same leakage, if you move a building around to a colder climate or a warmer climate or a windier climate, you will have a different airflow rate. So we have a built-in table of factors that's called the weather factor that accounts for that, that lets us figure out what sort of airflow rates we would get if we were mechanically ventilating. We also do some what we call source control, which is exhausting from kitchens and bathrooms. The various airflow rates are here. We have a few strange things, like if you have a fan that runs all the time, we have a lower airflow requirement than a fan that you might switch on when you enter the bathroom, or for a cooker hood that goes over the cooktop, that would have a higher airflow if you were to turn that on and off manually, and so on. So we try to account for some of the bigger sources of moisture and odors in the building through this sort of source control approach. Recently, we've got away from just thinking about dilution with ventilation and instead thinking about, well, what if we filter some of the air in a home? Surely that counts, right, as providing acceptable indoor air quality in some way. And so we've added a very simple procedure, which, depending on how good your filter is, allows you again to reduce that total airflow rate required for ventilation. So if you have a really, really good filtration system providing lots of clean air into the building, you can reduce the overall ventilation rate that's required. And the idea is we want to have the same exposure to contaminants in both cases. And roughly speaking, that's what happens here. And ideas like this are sort of blurring that line between air quality and energy use, because a big part of the energy use is heating and cooling and controlling the humidity of the air we bring in and out. If we can reduce that because we filter some, then maybe we can have a more energy efficient way of getting to acceptable indoor air quality. And that was part of the rationale for this sort of approach. So to be clear, this isn't in addition to providing the airflow. This is a substitute for. We also think about, well, what if you have fans that don't run at the same speed all of the time, varying airflow rates? Again, we don't have time today to talk about the engineering calculations, just to know that within the 62.2 standard, if you have a schedule that varies over a short time period, you can do some simple averaging. But because the concentration of contaminants in the space is inversely proportional to the airflow, you can't average over long time periods. And so we have a more sophisticated calculation method that looks into ways of having variation in the airflow, but still having the same exposure to contaminants. And some of this technique has been used to try and do some, again, energy efficiency measures by time shifting when we ventilate. In other words, you could ventilate when the temperature differences between inside and outside are small, ventilate less when they are big, so you get the same total airflow, the same exposure to contaminants, but hopefully you get to save some energy. And there's a whole IEA annex that sort of thinks about those sort of things, Annex 86, which had its meetings earlier this week that I know some of you were at. But in 62, we sort of embodied those calculations right in our standard. And, you know, we have these requirements about you've got to be exposed the same, no matter what your ventilation system's controls are. And we have some ideas about if you didn't ventilate for a long time, you could get very high concentrations indoors. And we want to avoid that peak exposure that we might term an acute exposure, bearing in mind that almost all ventilation standards are only looking at chronic long-term exposure to contaminants. So we have this limit for the peak exposure to account for that. We heard a little bit earlier this morning about there's some differences between new construction, where you can say things about energy like, let's have zero net energy homes for new construction. But in existing homes, that's not so simple. And we have the same thing here with ventilation requirements in the US, where an existing home, sometimes it is quite difficult to install an exhaust fan in a kitchen or a bathroom. So we have a way to comply, which is not the same as for new construction, where you don't have to meet sound ratings, for example. You can substitute exhausting from kitchens and bathrooms by increasing the total dwelling ventilation, airflow, and so on. And this just gives more flexibility when we're looking at ventilating existing homes and trying to bring them into compliance with the standard. And just a couple more slides on the residential side of things. There's a whole bunch of what we call other requirements that aren't necessarily, here is the airflow, right? There's things like, how sure are we that you've installed it right? So we have a requirement that the airflows are measured and verified. We have issues about if you install very, very noisy fans, people will not like it and they will turn them off. So we require the fans to be relatively quiet. Very recently, we've introduced a minimum filtration requirement. We use the US MERV reference here, but for those of you who think about infractions of PM 2.5, it's about 35%. So not fantastic, but, you know, small steps. Something that might be more relevant to multifamily construction is we have some special requirements for multifamily buildings. We have this thing called compartmentalization, which is the leaks of the interior partitions rather than the exterior envelope, where we're trying to limit transport of contaminants and air from unit to unit. So we have some requirements for that. Odd things about, we don't want leaky ducts. We don't want to recapture from an exhaust for our inlet. So we have ways of separating those and so on. And then a few odd things at the very end here that are you might consider to be safety requirements rather than air quality per se, things like requiring carbon monoxide alarms. Hopefully we never get carbon monoxide in a home, but it can happen, particularly in homes that burn fossil fuels inside them. Speaking of which, after an 8-year struggle, we finally do not allow what we call unvented combustion. That is things that are burning natural gas or propane or whatever fuel it is and not vented to outside. We do not allow that anymore. Now I'm going to spend a few minutes talking about ASHRAE 62.1, which is different in many, many ways and similar in a few. For example, in 62.2, we don't talk about designing the systems, but 62.1 is all about system design. And this is an order of magnitude more complex than anything we do in the US in a residential building. It's a very, very different approach to think about ventilation and how we specify it in a standard. There's a lot more information on how systems get designed, things like balancing systems, pressurization issues. They even consider what's happening in the outdoor air with regional air quality and so on. These ideas about you have to have different separation distances between a source and where the air is coming into the building. And so we have big tables that I've shown here that say how close they have to be together. In other words, it's going to be a lot more work, which is why most of the engineering that happens in ventilation in the US happens for the non-residential buildings, because you need to be an engineer to figure out all of this stuff. It is much, much more complicated than 62.2. It also introduces other concepts like the breathing zone. In residences, we basically effectively have an assumption that all the air is mixed up. But in commercial buildings, we do not have that assumption. And we qualify this thing called the breathing zone, and we have different requirements depending on the sort of building it is and the occupancy it is for how much airflow you have per person, how much airflow you have per unit floor area, and things like that. And these are all what are referred to as a breathing zone requirement. And there are relatively sophisticated and complex calculations for figuring out all these different ventilation zones in a building. Again, I don't have time to go into that. And it would probably take all day, honestly, if we would actually go through all the calculation procedures. They are quite tricky, right? And we think about effectiveness of ventilation. In other words, just putting 100 liters a second into a room doesn't necessarily count as 100 liters a second towards what's getting breathed from the 62.1 perspective. There's also something called the indoor air quality procedure. So rather than specifying you must have this airflow rate, this is a procedure that looks at different contaminants. And if you have an emission rate, you can calculate an airflow that's required to keep your contaminant below a certain level. So there are tables that contain various contaminants here with some design limits. That's the design criteria that you must meet. And you have to design a ventilation system that will keep the contaminants below these levels in the table. And we call that the IAQ procedure because we're not just specifying an airflow, we're specifically getting to indoor air quality equivalence. And it does include not just chemical contaminants, for example, but it does include things like perceived indoor air quality, which depends on things like if you were to survey everybody in this room, we don't all have to be happy about the indoor air quality, but most of us do, right? So we look at this fraction, the fraction of people in the room who think the indoor air quality is fine. It also requires that if you've said you're going to meet a concentration for a contaminant, that you actually do so. So you have to measure it. There's also calculations in 62.1 for what we call natural ventilation. So maybe you don't have a fan. Maybe you have deliberate openings in the building where the air is driven often by the wind, sometimes by temperature differences. And again, there's a rather complex calculation procedure that tells you what sort of areas you need to comply. And like 62.2, there's a whole sort of shopping list, if you will, of other requirements that might not directly tell you what the airflow is, but it includes things like, can you time average a varying airflow rate? What about demand control? You could have demand controlled systems that say monitor the CO2 in a space and would change the ventilation rate accordingly. Again, there are requirements for filtration, slightly different from 62.2 because, of course, they would be. They only require MERV 11 if the level of PM outside is high. And there's odd things like we don't have parking ventilation requirements in residential, but we do for large commercial buildings because they often have parking in them. And so there's a whole bunch of other requirements for 62.2. And I will finish up here by pointing out something that is a big difference between these two standards, at least in the US. ASHRAE 62.1 is the non-residential part. It's basically used in almost all jurisdictions in the US. It's embedded in what we call our model energy codes. They basically require that you comply with this when you build a commercial building. And I would say it's almost universal in the US for commercial buildings that they have a designed ventilation system. The residential case is very, very different. There's only a very few states in the country that actually require it, and then only new construction. There are non-minimum code things like the Environmental Protection Agency Energy Star buildings are required to be ventilated. Department of Energy Weatherization Program, all sorts of state and local requirements for often in the energy programs require ventilation. And it's just much less universal. So most homes in the US, and I think this is probably true in other countries too, basically don't have any mechanical ventilation in them. So it's a very, very, very different thing. That is slowly changing. And I would say that in the last few years, I think all of us in the room probably know that there's been a lot more interest in indoor air quality for the obvious reason. And we're finding that there's many, many more jurisdictions are interested in figuring out what to do in people's homes from a ventilation perspective. And I'll end there, and hopefully we didn't eat too much into your break time. And hopefully we can maybe have one or two questions.
Thank you very much, Iain, but unfortunately, time ran out, so
that's okay. People can find me and ask questions.
During the break. Okay, so thank you very much, Iain, again. Thank you. And we should have a coffee break from now. I think it will. We will start again 11:15. 11:15. Okay, thank you very much again.